wasn't solution to number 1. Homework 1? There's solutions to 1.
There's solutions to all the homeworks up right now.
Okay, well, let me. Okay, so let's get back to wrapping up diffusion, right? So before we talked about diffusion in single species self-diffusion, on Wednesday, we started to talk about interdiffusion, right? And A diffusing into B and B diffusing into A, right? And we brought up the idea that the rate at which A moves through B is not necessarily the same as the rate B moves through A, and that the diffusivity itself can be concentration dependent, and that because if we have vacancies, vacancy diffusion is the prime mechanism. That means if we have a balance in the rate at which A moves through B and which B moves through A, it means we have a net flux of vacancies from one side to the other that either need to be created and destroyed, and that a net flux of vacancies means that this interface is not stable with respect to its position. The interface is going to move, and the lattice planes themselves are going to move. Right? And so if the lattice planes are moving, we have to consider the diffusion of a species relative to the lattice plus the convection of the lattice, right? So that means that things become a little bit more complicated, right? So first, the fact that if our diffusivity becomes a function of concentration, it means our Fick's second law becomes more complex, right? So we've got more complicated PDEs, right? So there's no real good analytical solutions to these, except for very particular cases. The actual solutions to the differential equations are not so much of interest to me for this class. It really is a class in and of itself. What I think is much more relevant is understanding the general physics of it and thinking intuitively about what's going to happen and what's going to move where and at what kind of time. Okay. So if we consider this situation where we have two phases that share the same crystal structure and we have a completely missable A-B phase diagram, right? We're going to have B diffusing into A and A diffusing into B. We're going to develop a composition profile. And we talked about how there's going to be a net flux of vacancies, right? Due to the fact that A, in this case, moves faster than B, right? So if we have A moving, right, for every A that moves, we need to have B moving this way plus additional vacancies going this way. So we need to create vacancies over here, and we need to remove and destroy vacancies over here, right? How do we create vacancies and how do we destroy vacancies? Well, we have climb of edge dislocations. We have grain boundaries and free surfaces, right? And external surfaces, right? These are all sources for vacancy creation and annihilation, right? So jogs are, the climb of edge dislocations are a primary source and sink for vacancies, right? So if we move a vacancy over into the, so that the atom that's on the slip plane of a edge dislocation here, this atom jumps into a vacancy. Now the edge dislocation, the dislocation line has climbed one plane, and we've annihilated a vacancy in our system. We can create a vacancy by having this atom hop over to here. We've created a vacancy, and our edge dislocation line has moved down one plane. Okay, so we talked a little bit about the importance of climb for hardening. This is just informational. It's not important for this class. You'll talk about it more in mechanical properties. Right. So what is important, though, is to understand how this creation and annihilation of vacancies translates to the motion of lattice planes, right? So if we have vacancies moving this way, right, and we're eliminating vacancies, essentially we're going to be eating away these planes, right? As this plane, as these atoms hop into the arriving vacancies, these planes here are going to shrink and be eaten away. And if we're creating vacancies, we're adding new planes here. So if we're removing lattice planes over here and adding lattice planes over here, what this means is that these lattice planes are slowly traversing through our system. And the set of planes that was our initial interface is going to be moving with a velocity this way, right? And it turns out that the rate that these atomic planes move is just a scalar multiple proportional of the rate of vacancy creation or annihilation, right? But the physical picture here is what's important. If I'm creating lattice planes over here and I'm removing them over here, that means everything in between is, all of these lattice planes are moving with a velocity in this way, right? That's moving in the same direction as the excess dislocation flow. That's the important part, okay? So we can create an expression after doing some geometric analysis, right? And we get a expression for the velocity of our diffusion planes that's going to be proportional to the difference in diffusivity between A and B, right? And this is what's known as Darkin's first equation, right? Right. It's really important from a fundamental physics and analysis point of view. It's not super important for practical analysis, right? Because we don't care about the movement of lattice planes deep in a sample, right? What is important is understanding as to how to apply this to develop expressions for interdiffusion. Okay, so this is a super important equation that you'll probably never have to do anything with, right? So if we think about Fick's second law, we want to recreate a term of flux that's the total diffusion, right? So when we talked about Fick's, the flux before, when we were talking about Fickian diffusion, we assumed that that lattice plane stayed put. And so that any flux that crossed it was completely due to the diffusional flow relative to the lattice. Now we know that this plane is moving, so we have to account for that. So we're going to make a spatial reference, right, which is a thin slice that stays put in space. And we're going to say we have a total flux of atoms through this slice that depends on the diffusional flow and the convection of the lattice through this, right? And this is really, really counterintuitive the first time you think about this. We don't normally think about the crystal lattice moving through a solid. But when we have diffusion, that's exactly what's happening. At least when we have interdiffusion between two species. So if we write our diffusive flux, and then we combine it with the movement of the lattice, it got cut off on this slide somehow, but it's up here, right? We have an expression for the total flux. We have the diffusion plus the lattice convection. And then if we combine this with Darkin's first equation for the velocity, and we do some rearranging, a little algebra, we end up with the equivalent of Fick's first law for the total flux, right? And it's got this interesting form. It's the mole fraction of B times the diffusivity of A plus the mole fraction of A times the diffusivity of B, right? And so what we do is we wrap this up. This is this intrinsic diffusivity of A, the intrinsic diffusivity of B. They all get combined together to wrap up into something that's called the interdiffusion coefficient, right? Which is given by this tilde here. And then we recover a relationship that says the total flux is equal to the interdiffusion coefficient times our concentration gradient of A, right? And this allows us to write that form of second law that we saw before. So this tilde is really important because this is the interdiffusion coefficient, and it has an input from both the diffusivity of A and the diffusivity of B, right? Right. So what are the key takeaways? The key takeaways for interdiffusion is I have a net imbalance between the rate of A and the rate of B, which means vacancies need to be transported as well, right? That transport of vacancies means that my lattice moves, my lattice convects. That lattice convection means that my total flux is my diffusional flow plus my convection of my lattice, which means we need to express something called this interdiffusivity that accounts for this. And Darkin's equations explain that scenario. Okay, that's the chain of logic. Don't get lost in the details of the math. Okay.
I'm sorry, but can you go over that again real quick? I had to, my phone rang. I had to shut it up, and I missed that.
Okay. Thank you for your honesty there, Kevin. So the chain of logic is this: when we have two diffusion species, A into B and B into A, we have a diffusion couple. The rate of diffusion of A and B and B and A are generally not going to be equal. That means we have, since diffusion is vacancy mediated, it means we're going to have a net flux of vacancies from one side to the other. That net flux of vacancies from one side to the other means that we're going to have a convection of the lattice. So when we think about diffusion in a couple, we need to consider both our diffusion through the lattice plus the convection of our crystal lattice. Okay? So then there was Darkin, who worked out all of this. And he showed that the velocity of our lattice planes is given by this expression here, which is proportional to the difference of the diffusivities, right? And then he went a step farther and said, okay, I can plug this into my flux equation here, total flux, and I get a term out front that looks a lot here like Fick's first law. So if I just pull all the stuff that's different out, I get this term, and let's just call this the interdiffusivity, right? Which relates how A and B diffuse into each other. And this interdiffusivity, when we just consider it, it returns us back to something called the total flux, right? So we have a Fick's first law and a Fick's second law that look like what, for interdiffusion, that looks like what we saw before, right? Just the definition of the diffusion coefficient out front is different because it accounts for both A and B. That's a slightly longer version of the same story that I just told. Okay, so what does this interdiffusivity look like? Well, you can think of it as a type of average between the intrinsic diffusivity of A and B, in this case, nickel and copper, right? So when we have no copper, or when we have no nickel, right? When we're 100% copper, right? We have a single nickel bouncing around. When we have pure nickel, we have a pure copper bouncing around, right? So let's think about this. So this line represents the diffusivity of copper, right? This is the diffusivity of a single atom of copper in copper. This curve here, this point down here, represents the diffusivity of a single atom of copper in pure nickel, right? And the diffusivity of a single atom hopping around of copper is going to be dependent on the concentration, right? This, we have the same picture for the nickel. And then now what happens when we have, when we're thinking about how fast we're going to get interdiffusion between the two, right? If I have a block of nickel and a block of copper stuck together, these curves describe the hopping of individual atoms, individual copper atoms, individual nickel atoms. But what I want to know is how fast are they going to diffuse into each other? And the interdiffusion here gives us that way of averaging these two together, right? So right, so that's really what's meant by the interdiffusion coefficient, right? It tells us how fast these two species are going to diffuse into each other. Okay, so that's just the mathematics, right? So now we need to think about the physical effect. And the physical effect of this was studied by Kirkendall and is named after him, right? And so the experiment that Kirkendall did, right? He said, let me take brass, right? This is copper plus 30 weight% zinc. And I'm going to embed it, first wrap it in molybdenum wire, right? Why did he pick molybdenum? Because molybdenum has no solubility essentially in copper, right? So there won't be any interdiffusion between this molybdenum and copper, right? So these molybdenum wires are completely inert in this system. They're not going to dissolve. They're not going to diffuse. There's going to be no diffusion. Okay. What he did then was electroplate high purity copper over this whole system. So there was a very perfect bond, right? And then he did diffusion and then cut the sample in half and found that over time, these molybdenum wires got closer to each other, right? Because the conclusion of this is that the zinc diffused out of the brass faster than copper diffused in, right? And so I have a net transport of material out. And so these wires got closer together. Okay. Note, the figure in your reading is wrong. The figure in the book is completely wrong. It shows the wires moving the wrong way. Okay? So I can't fix that what's in the textbook. But this is what should happen. Okay? So this experiment was actually really important because it provided the conclusive evidence for the vacancy diffusion hypothesis, right? So before then, there were three possible contenders: vacancy diffusion, which we now know to be true. There's also, you can think of atomic exchange, two atoms just moving past each other and swapping places, right? That's one possibility. And then there's a ring mechanism where you can have three atoms rotate, right? They can move in a clockwise motion, which takes slightly less energy than the atomic swapping or atomic exchange, right? There was theoretical reasons to support vacancy diffusion, but there was a lot of adherence to the exchange and ring mechanisms as well, right? So you have to remember that a lot of what was happening in material science could not be proved until the development of electron microscopes in the 50s, right? The TEM proved a lot of things, right? So before the 1950s, the dislocation theory was completely just a theory, right? And in fact, I've got some metallurgy textbooks from the 40s and 50s, and they're peppered with statements that say things like, if the dislocation theory is proven to be true, right? Meaning that there were a lot of people who felt that the concept of a large number of defects in crystals was absurd, right? They thought it was just a mathematical convenience that it explains so many things. And the same thing with vacancy diffusion, right? But in 1947, the series of experiments done by Kirkendall really showed that vacancy diffusion is true. Because if we had an atomic exchange or a ring mechanism, these wires wouldn't move, right? We had a definitive experiment that showed that all of the other contenders couldn't possibly be true, right? So if we don't have if we think about what happens during the interdiffusion experiments, right? What happens if we can't actually eliminate all of the vacancies in time, right? We can't, the flux of vacancies is too high, and we can't actually eliminate them all. Well, what happens is we start to get pores, right? So if we have an initial contact plane, right? And in the diffusion literature, you'll see this is called the metano plane, right? After the Japanese scientist who did the first analysis, quantitative analysis of interdiffusion, and found a way by measuring the composition profile as a function of time to be able to get out the diffusivities of A and B and calculate the interdiffusion, right? So what we see is that over time, if we have a set of inert markers at this interface, we have a net flux of vacancies, right? Our interface moves with time. And if we can't eliminate the vacancies fast enough, we get pores and voids that form, right? But the important thing is that our interface moves, right? And this can be measured. So let's think about this. If I have nickel and copper, where are the voids going to form? Right? So this is unfair. I'm asking you to think about something after the...
Well, I'll try a crack at it.
Okay.
So we have the diffusivity of nickel and copper shown here.
Mm-hmm.
Wouldn't the voids form?
So think about it. So what's faster, copper and nickel or nickel and copper?
It looks like nickel and copper because the
right.
slopes,
okay. Yeah. So the
slope's larger.
Yeah. So the diffusivity of a nickel atom in pure copper is higher than the diffusivity of copper in pure nickel.
Okay.
Right?
So I'm thinking, wouldn't this happen when there was a? Go back to that chart.
Okay.
So would the voids form when there was a higher fraction of nickel because there's more rapid diffusivity that way?
Okay. So we can pop it on our shift here, right?
Mhm.
So we said what? Nickel is going to diffuse faster than nickel into copper is faster than copper into nickel, right?
Uh-huh.
So this now is the nickel rich
Uh-huh.
and copper rich, right? Did I say that right? Yeah.
Yes.
Right. So
Oh. Okay.
right? So let's take a look.
How fast is this process?
So at high temperatures, this takes a while, right? So to do these diffusion experiments, basically you'll make a couple like this and you'll put it at high temperature and let this sit for days, right? This is hundreds of hours at very high
Why it
temperature,
took so long to prove the theory.
right? Right. So this actually is a really interesting case study, because this nickel copper is one that is a diffusion couple that everyone is familiar with.
So what are the voids on this chart?
The voids, what do you mean on the chart?
On the image on the right.
On the image, right, the voids are where vacancies clustered together to form pores, because they couldn't be eliminated by climb fast enough.
So it's kind of on the boundary?
So it's not on the boundary, it is where the boundary swept. So the pores tell you essentially how far. You can think about the pores as being a visual indication of how far the diffusion moved, the boundary moved, right? Okay. So if you had inert markers
based on
here,
that chart, based on that chart you just showed us on the last page, since the nickel has a faster rate of diffusivity, the pores will be pushed towards the nickel.
Right. So right. So the net. So once you get voids like this, this is essentially a permanent situation, right? You can't really fix. You can't really fix this, right? Right. So think about this picture, work it through in your heads, right? And try, and we'll talk about this again on Wednesday, right? But I just want everyone to think about it a little bit and think, does this picture jive with what you see here and what you see here? Because it's really easy, what you see here, it's really easy to get yourself confused and say something backwards, right? So just think about it. We'll walk through it again on Wednesday. Okay. But this couple, this nickel copper couple, right? This is a US quarter. Right. And in fact, when I used to teach the physical metallurgy lab, the senior level lab 5441, we would do this experiment. Right. You have to do it in vacuum because the nickel oxidizes really, really, really fast. Right. And in fact, that was part of the fun of it, because in that class, the students would develop their own experiments, right? And so the first time they would do it, they would try and do this diffusion in air. And at high temperature and air, the nickel just completely corrodes, right? You get nickel oxide that grows at a much faster rate than the diffusion, right? So it's a fun kind of way of harmless kind of way of letting people screw something up. and learn from it. Okay, so think about this. All right, think about this chart. It seems a little counterintuitive. And think about this picture, right? And try and answer for yourself where the initial interface was, where the Metano interface would be now, right? Okay. Yeah, so zinc and copper. Right. So Professor Locke did that in the sophomore lab in 2010. Okay. Cool. Okay. So the last little bit is we have high diffusivity paths, right? There are some short circuit paths for diffusion, right? Actually, we'll stop there for today. Everyone's kind of brain dead. And there's some subtleties that I want to talk about and not quite be rushed. So on Wednesday, we'll wrap this up. And then we'll talk about high diffusivity paths. And then we'll start talking about solid state phase transformations a bit. I'm going to hold off on diffusion in polymers for just a bit when I talk about solidification and vitrification, because the diffusivity is also tied up in the rheology of polymers. So I'm going to get to it, but it felt a little misplaced when I was putting the notes together for it. So I'm going to hold off on the diffusivity in polymers, but I promise we will get to it. Right. So let's stop there. We're going to wrap up for today, and everyone take a much needed rest, so there won't be any homework for this class.
The bad news is a lot of us have another exam this week, actually. The good news is it's in my opinion, the easiest class for us MSE people.
Good. Well, it's not good that you have another exam, but I'm glad that I'm not going to be piling on anything with extra homework. Right? The diffusion is a good spot for that, because I don't expect you guys to do a lot quantitatively with the diffusivity, right? I want you to understand it sort of intuitively and think about physically what's happening and the meaning of things, not necessarily being able to solve quantitative problems with diffusion. So this is a good spot for a homework break. So we'll talk to everyone Wednesday, and try and get some rest.